We'll start with these wildcard mask problems. Wildcard masks are really cool. They've been around forever, really since the dawn of IP addresses. And the issue that we run into with wildcard masks is that they don't always select the exact range of addresses that we're looking at. Well, it starts with some ranges here that really precisely line up with the boundaries we have in binary. So we have 10.0.0.64 through 10.0.0.79. So if I wanted to write a wildcard mask for this, I want to write out the first address in binary. Once I have that first address written in binary, right below it, I can write the last address in binary. And then what I'm going to do is I'm going to compare the bits. So I'm going to start with my bits on the farthest left, and I'm going to examine them until I find bits that no longer match in both addresses. So here, the 29th bit is the one that is no longer the same in both the first and the last address. Well, this works out very nicely for us because we have a setup here where the first address has all zeros in the portion we're going to make the wildcard mask, and the last address has all ones there. So this is kind of like subnetting, except in subnetting, we are actually concerned about network addresses and broadcast addresses. With a wildcard mask, we no longer are concerned so much about the network and broadcast address, more so just about the first and last address in the range. So here what I can do is I can make those last 4 bits my wildcard mask on bits, the 1 bits there. And what that will do now is it will give me a range from 10.0064 through 10.0.0.79. So then what I would write then to get that range of addresses is 10.0064, 0.0015. Let's take a look at another one. 10.0.1.88 through 10.0.1.95. This is a little bit odd range of addresses here, except I explicitly picked this range of addresses because it works out very nicely to calculate a wildcard mask. So we never really know if our wildcard mask is going to work out until we explicitly write it in binary, or we have a really keen sense of binary already behind us. So we'll write out our first and last addresses here. Once again, I set this up so that we can see that in that first address, there's a series of zeros at the end of that address. And if we start comparing those from the leftmost bits of the address, we compare it, we're going to see that the 30th bit here is the bit that's different in both addresses. So we're going to take those last 3 bits, and those are going to become the bits that we use for our wildcard mask. Effectively, what that's saying is with the wildcard mask, we're saying to the router, pay attention to the first 29 bits, and then the last 3 bits, ignore those. So if the address that we're trying to select with this range has the first 29 bits that are identical to these 29 bits, then we select that address. If it doesn't have the first 29 bits that are the same, then it's not selected. So really, those last 3 bits here, we're just going to tell the router to ignore those bits when we use a wildcard mask of 7. So then our address and wildcard mask become 10.0.1.88 with a mask of 0007. And that will select the range of addresses from .88 through .95. So let's take a look at another example here. This time we're going to use an address 10.0014 through 10.0099. Now this address range is not nearly as neat, and I've chosen it to be not neat and clean with the wildcard mask explicitly for this example so we can see how this unusual situation works out. So we'll write my first address out, we'll write my last address out, and then we'll compare my values of the bits in the address until we find one that doesn't match. Here it is the 26th bit that no longer matches. So if we use that then, like we have been to create a wildcard mask, we would put 7 bits in that wildcard mask. And what that would do for us though, is that means that our very first address in our range will be 10.0.0.0, and the very last address in the range would be 10.0.0.127, and this exceeds our range of .14 through .99. So what we need to do is something different. We can't use this methodology exactly like this in order to calculate the wildcard mask for this weird range of numbers. What we're going to have to do is break this up into smaller components so that we can get the entire range that we're looking for here. This does get a little messy. So when we're writing wildcard mask in an ideal world, we would choose address ranges that are nice and neat so that our access lists can be nice and neat, but there are occasions when we have to do this weirdness. So what I do then is I'm going to push my last address in my range way down to the bottom of my page, and then I'm going to start with the first address and examine it. In the previous examples that I gave, what we saw was that that first address always ended in a nice, neat set of zeros. And here we kind of have that, except that that first address only ends in 1, 0. So what I'm going to do is simply add 1 to my .14 address to get .15. And what I see there then is if I compare those two addresses, the first 31 bits are exactly the same, and it's just that last bit that's different. So I can start writing my wildcard mask then for our range of addresses here and start with 100014 and apply a mask of 0001. What that'll give me then is a range of addresses of 14 and 15, giving my next address as 10.0.0.16. So I'll convert that to binary, and now we'll examine that address. And this time, if we look at that address, the last 4 bits of the address are zeros. And this works out very good to our favor, because what I'm going to do is just flip those last 4 zeros to be 1s, and then I can use that then to compare the two addresses, see that the first 28 bits are identical, that the last 4 bits are completely different here, and now I can write my wildcard mask as 0.0.0.15, and that will select me a range of addresses from 10.0016 through 10.0.0.31, leaving .32 as my next available address. Now this trick is producing some really nice results for us. Now if we notice, our address ends in 5 zeros. So what I'm going to do now is flip those bits. I'm going to write the same exact address as I wrote above, except this time I'm going to take those last 5 bits. I'm going to flip the zeros to 1s. This kind of looks like what we were doing with subnetting when we were calculating the network address and the broadcast address. Network address is the first address, broadcast address is the last address, except in this case, when we're working with the wildcard mask, I don't care so much about calling it a network address and a broadcast address. I'm more concerned about selecting a range of addresses that's interesting to me. So what I do now is I add the wildcard mask of 00031 to that, making my first address the .32 and the last address .63, making the very next available address 64. And notice what happened again. Now I end with a string of 6 zeros at the end of my address. Well, now we're starting to get close to 99, or much closer to 99. And the reason that I see that is I see right now that the first 26 bits of my first address, that .64 address, are the same exact as the first 26 bits of my last address. So when I start to notice this, what I can do now is I can start to compare the first address I have and the last address and see what kind of efficiency I can get and what kind of mask I can create to accommodate this network. So here, if I put 6 bits in my wildcard mask and make a wildcard mask of 00063, what's going to happen when I flip those bits, those 6 bits at the end of my address to 1s, is I'm going to get an address of 10.0.0.127. And that exceeds the .99 address that I'm looking for as my last address. So when this happens, what I need to do is make my wildcard mask 1 bit smaller. So I make that mask 1 bit smaller, and that makes it the same exact wildcard mask as I had before. So my first address is .64, my wildcard mask is 00031 again, making my last address 10.0.0.95, making the next available address 10.0.0.96. Hopefully you can realize between 96 and 99, we only need 3 addresses there. So what I can do then is compare the first address and the last address, just like I did in those real simple examples. And now I do have here the first 30 bits of my address are exactly the same in my first and last addresses. It's just those last 2 bits that are different. So here I just apply a wildcard mask of 0.0.0.3, and 96 plus 3 gives me that last address of 10.0.0.99. So in order to get from 10.0.0.14 through 10.0.0.99, I need 5 different wildcard mask statements to accommodate that. Other wildcard mask combination that what I would do here would either put me at a starting address below 14 or end me at an ending address above 99. So we need these 5 statements in order to accommodate that range of addresses. Now, like I said, this is not a common practice. I don't recommend this. There are always very unusual circumstances that happen on networks, and you just sometimes have to do goofy things like this. But it's a good idea to avoid setting up a system where you have to choose this very bizarre range of addresses. The best way to do it is if you do have to select addresses to filter with an access control list, I highly recommend that you put all those addresses in one range that fits neatly into a wildcard mask, instead of having to do this goofiness with all kinds of wildcard masks and weird calculations.